Morning. It's a great pleasure to welcome Benoit Cerutti this morning at IAP. Benoit is an expert in high-energy astrophysics and especially in the modeling of the particle acceleration and the associated radiation in the vicinity of black holes and neutron stars. He prepared his PhD at Grenoble with Guillaume Dubus, and he made pioneering work on the high-energy gamma-ray emission from compact binaries and especially the time variability of this emission. And then he moved to the United States. He was a postdoctoral fellow first at Boulder and then at Princeton, and he developed very accurate and realistic numerical tools to model particle acceleration, especially in magnetic reconnection layers and the associated radiation. And his main application, which had a big impact, was the interpretation of the flares, the recently discovered flares from the Crab Nebula. And he got a position at CNRS in 2015, and so he's working at the Institut de Planétologie et Astrophysique de Grenoble.
That's right.
Okay, and so today Benoit will discuss recent work on the emission of pulsar, and especially at high energy.
Mm-hmm.
Thank you.
Absolutely.
Benoit.
Thank you very much. Would you like to switch this off, maybe? All right. Right, so 2018 is actually a special year in astrophysics because, as you know, this was 50 years ago that pulsars were discovered for the first time in the form of an unusual, rapidly pulsating source in radio. So you can see this first paper, as you can see the date, 1968, in February, actually, so we have to wait a little bit more for the anniversary of the publication. But as you can see, very rapidly, they interpreted this signal as coming from pulsars, a neutron star. The name pulsar did not exist at the time yet, but as a rapidly rotating neutron star. The reason for this is this very coherent emission of pulse of light in radio, very rapid, typically from milliseconds to hundreds of milliseconds to seconds for the slowest rotators. And so this was quickly realized that neutron stars could be producing this because neutron stars were already predicted. They were already predicted in the 40s, shortly after the discovery of the neutron. And so just to give you an idea in numbers, so that we all talk about the same thing, is that neutron star is about 10 kilometers in radius. It has supernuclear densities, about 3-4 times the nuclear density. So you have roughly a solar mass in this sphere, and the magnetic field, which plays this very important role in the emission, is from 10 to the 9 to 10 to the 15 Gauss. And so from these very first observations, people realized, well, somehow what's happening here that is producing the light, it must be a beam, very narrow beam of radiation that is pointing towards us in a fashion of a lighthouse, a cosmic lighthouse. So kind of the overall idea of what I'm going to talk about today is an accurate modeling from first principle using numerical simulations to try to understand how the high energy light, so not the radio but the gamma rays, and I will explain you why gamma rays in a minute, what's the shape of this beam and what is producing this beam of light that we observe. So the thing that you have to realize with neutron stars, they are, amazing objects for astronomy because you can do very precise measurements. So you can do very precise measurements of this period. So you can measure very accurately the rotation period. So if you have the rotation period, you know exactly how much energy you have in the form of rotation. And the other thing that you can measure very accurately, this is what you can see on this graph over here, is that you can measure the slowing down of the pulsars. So the pulsars separated more and more in time. It's very slow, but you can measure this with very high accuracy. So this is what I show here as the time derivative of the period, of the rotation period. And if you have these two elements, that again you can measure to very high accuracy, you can have an idea of the power. So you know exactly how much power the neutron star is injecting in the environment. This is very unique for a compact object, because if you're talking about a black hole, for instance, you don't really know how much power the black hole is going to release to the environment. So you have a very clean system. That's one of the reasons why I like this problem in particular. And you can measure two characteristic quantities here, which is the age of the system, which is basically a ratio of this p over time derivative of the period. And you can measure with this combination also of p and p dot the magnetic field. And by doing this, you take all the 2,000 pulsars that we know, and you can put this in a diagram where you see the rotation period over here and this time derivative period. So the power and the rotation period. And each of these dots is an object. So don't worry about the color right now. So these are the guys that are seen in gamma rays, but I will come back to this. You see there's mostly one big population, which is shown here, which is for fiducial number of rotation period of a fraction of a second, 100 milliseconds typically. And they will have a magnetic field of the order of 10 to the 12 Gauss. These are the population of young pulsars, such as the Crab pulsar, that we think are born from the collapse of a massive star that would be typically from 1,000 years old to hundreds of thousands of years. If you look at the lower hand of the diagram here, you have much faster rotators. They have a rotation period of a few milliseconds, so much faster rotators. But on the other hand, their spin-down power is much less. So they are, in fact, much older systems that are found in binary systems. They are found with another normal star that is accreting, and whose the compact object is accreting material from this star. So the scenario here is that we think that the neutron star was spun up by the accretion from the star. Now, if you look at the other extreme of the diagram over here, we have just a few objects. We have maybe a dozen or so, and they are much slower rotators over here, but they are also much younger system, and they have much higher magnetic field. They are known as magnetars. They have magnetic field of the order of 10 to the 15 Gauss. So this is kind of the general pictures of the type of neutron stars that we have in the galaxy. In fact, I will be mostly focusing on these two populations over here, which are the population where the reservoir of energy is in the form of rotation. So there's no magnetic field. Well, there's magnetic field, but it doesn't dominate the dynamic of the neutron star. So as I mentioned earlier, the gamma ray light plays a very important role for pulsar physics. And the reason is illustrated here. What you can see here is a broadband spectrum of one of the most luminous pulsar, which is a Crab pulsar. You see there's 18 orders of magnitude in terms of frequency over here, from radio to TeV gamma rays. As you can see here, is that the radio plays a completely irrelevant role in terms of energy. Even though they were discovered there, because we have much higher sensitivity there, we have much larger number of photons, in terms of energy they count for nothing. However, if you look at the gamma ray band, you see that most of the power, 10% and more of the power, is dissipated in form of gamma rays. So it means that somehow these objects are extremely efficient accelerators of particles, because you need to accelerate particles to produce gamma rays. And there was a revolution in the gamma ray band that started in 2007, which is still going on today, with the launching of the Fermi-LAT, which is a gamma ray observatory in space that is observing in a range of 100 MeV to 100 GeV, which is fitting exactly in this window that I've showed you before, where gamma rays are very bright, where pulsars are very bright in gamma rays. And sorry, so if I come back here, this is a map of the entire sky in gamma rays, so you can recognize the galactic plane over here. And this is the same map here, we've only shown with, in color, the known pulsars discovered by the Fermi-LAT. So before Fermi-LAT, we knew, I think, 6 pulsars emitting in gamma rays. With the Fermi-LAT now, I think it's close to 200 systems that we know. And I will show you what we are seeing, what kind of the characteristic observation that we can see, and that we are going to try to explain here. So I'm going back to this diagram, this pp dot diagram. And what the Fermi-LAT is seeing is these two populations. It's probing this young population of stars, high magnetic field, rapidly spinning. And the case of this millisecond pulsar, so much lower magnetic field, but also spinning much more rapidly. So what I mean by this is that this is the system which are powered by the rotation energy of the system, of the star. I told you also that these guys are very efficient at accelerating particles, and this is the proof of that. So you can see over here on the x-axis the spin down power. So this we know very accurately. So we know how much power the star is losing. And on the y-axis here, so by the way, this is regardless of what we see or don't see. We know how much it's lost. We don't see all of it, but we know exactly how much. And in terms of radiation, the gamma ray band, this we can measure with Fermi. We can measure, so it has to be below, of course, this total power. There are some uncertainty. So for instance, this guy here is more than 100% efficiency. This is an outlier, but most of them are somewhere around a fraction that represents 10%. So 10% of the spin down, of this total power, is going into high energy particles and is going into high energy gamma ray. Yes, this is extremely efficient in this sense. So sometimes it can be more than 50%. The other two elements that we see that are very robust from one pulsar to another in gamma rays is on what you can see on the left-hand side. This is the pulse profile. What you can see here is three different pulsars that we call the light curve or the pulse profile. They are all always different. So you can tell which pulsar is which just by looking at the light curve. Maybe not by eye, but by analysis. They are always slightly different, but in maybe 75% of cases, you have two pulses of light per rotation. Not one, you have two. And in many cases, they are separated by half in phase. So as if you had two beams that are separated by 180 degrees from each apart. So that's one element. So it's trying to tell us something, that's something simple and robust in what's going on close to the neutron star. And the other element, which is still a puzzle that I will not discuss so much, which is still an open issue, is the form of the spectrum. The form of the spectrum in the GeV band, so the high end of the spectrum, it's kind of peaking somewhere around a few GeV, and then it's rolling off exponentially, or sub-exponentially in some cases. And this peak energy is almost always the same, regardless of it's a young pulsar with 10 to the 12 Gauss, or an old system with 10 to 9 Gauss. This is very puzzling. But something, again, robust and universal. So the main question I'm going to try to address here is to try to understand, okay, how does this engine work? How this energy is released? How is this energy then transferred into energetic particles? So how particles are being accelerated? So we can learn more about the physics of particle acceleration. And if we want to connect to observation, we need to also model the gamma ray emission. So how is this all connected together? And to answer this question, like very, I would say maybe practical questions, we need to answer more fundamental questions, which sounds fairly straightforward. The question is, I have a sphere which is magnetized and is highly spinning very rapidly. So kind of a rotating magnet. What happens in that case? Well, it sounds like a trivial answer. There is an answer to that. But as I will show you, what makes things complicated is that there is plasma in the magnetosphere close to the neutron star. There are plasma processes that are going to complicate the picture. But the overall, I would say, dynamic, or how we understand the overall electrodynamic of pulsars is, I think, quite simple to understand. So let's go through this step by step. So let's imagine a very simple case, which might be familiar to you, which is the case of a Faraday disk. So imagine that I have a disk that is perfectly conducting. So my electric field inside the conductor will be 0. If there is no net charge, it will be 0. Even if I put a magnetic field, nothing will happen. But now, if I add rotation to this disk, let's say if I let it rotate around this, from the rotation axis of the disk, with a uniform magnetic field with a constant angular velocity here, I will polarize my disk, because you will induce an electric field inside the plate, inside the disk. There will be the cross product of this velocity cross the magnetic field. So it means, in practical terms, in this particular case, that you will have a radial electric field pointing towards the center. So you will have a net positive charge on the outskirt and a net negative charge in close center. Of course, the total charge is the same, it's 0. So it's just an analogy to the case that we're interested here, which is the sphere. And in this case, oh, okay, so before I move on, so it means that if, what I want you to say is that you have, in other words, you have a potential difference between the center and the outer skirt of your disk. And it means that if you put a wire here, there will be current, in principle. So for the case of a neutron star, that's kind of the basic model of how a neutron star works. And this will be important, all these elements, for understanding the acceleration of particles later on. Imagine now the spherical case. Well, that's basically the same idea. I took, for now, a uniform magnetic field. Then I will produce, I show only here the poloidal electric field E theta, but there's also a radial component. But for the discussion here, it's this component that is important. And the fact that there will be a similar electric field, and there will be a potential difference between, between the equator and the poles. So it means if I manage to put a particle from here to here, they will get an enormous amount of energy, which I will precise in a minute. For a more realistic case, if we go to a higher order of complexity, in the case of a neutron star, you can put a dipole field. And the picture isn't changed, just the actual expression for the electric field changes. But you will polarize your star in the same way. So you have a net positive charge here and a net negative charge over here. And this is the case, I have to say, that you have an aligned dipole. So the dipole axis is aligned with the rotation axis, which is the case that I'm going to go through, the axisymmetric case for the discussion. But for the realistic case, I will show later on a misaligned case. So in the same case as for the plate, I will have a potential difference between the pole and the equator. And if I put numbers now, for the case of a neutron star, like a crab-like, like this young population, you plug in 100 milliseconds and 10 to the 12 Gauss, you will have like something like 10 to the 18 volts. So in principle, if I manage to bring a particle from here to here, I can get to almost ultra-high energy particles. Okay? And if I change the parameter, I say I have a young magnetar, I take 1 here, 1 millisecond, and I take B to be 10 to the 15 Gauss, I can go easily to ultra-high energy cosmic rays. But that's not what's happening, at least not exactly. The reason is, and that's what I said earlier, plasma happens. There will be plasma processes happening in the magnetosphere, which complicates this simple picture. Because you have this strong electric field at the polar cap, you will start to extract charges from the surface of the star. Remember, you have a crust with, mostly iron. You have electrons and ions. The electric field is so huge that, in fact, you're going to pull off charges. You're going to accelerate these charges, extract from the surface of the star. And the lightest element, electrons, will accelerate like crazy. Remember, you have this huge potential drop, so they will get to very high energies very quickly. But as they do so, they will start to follow field lines, but these field lines are curved. And so this slight curvature of the field line will induce curvature radiation. And this curvature radiation that will be happening very close to the star, this gamma ray, is in a gamma ray band, will be absorbed almost instantaneously by the huge magnetic field. And this annihilation by the magnetic field will produce an electron and a positron pair. So you begin with one electron, and then you have one pair. And this process continues, so this pair can radiate through curvature or synchrotron radiation. and produce more gamma rays, and so on and so on. So you have a cascade, an electromagnetic cascade, that is breaking your vacuum. So in a sense that the nature wants to kill this electric field, it will extract as much charges as it can to kill this electric field at the surface of the star. So in other words, to break the vacuum. So in fact, you should imagine this neutron star with this magnetic field, not in vacuum, but filled with a plasma, mostly of electron and positron pairs, so light plasma. Now let's look at further away from the neutron star. So I have shown here again an axisymmetric case where the dipole field is aligned with the rotation axis. So the plasma, if we look at bigger picture, so in first order it will be uniformly injected in all field lines. So it's not exactly true, but for discussion it would be enough. So you have to imagine this flow of electron and positron pairs. So if I look at this one, well, they will just be trapped in these closed field lines. In principle, all the field lines of a dipole are closed, except if you are very close to the axis. But this will not happen here, because there's another element here which is important, which is the light cylinder radius, which is defined as the moment that if you want to co-rotate with the star, so if you are an electron sitting on the field line, you want to co-rotate with the star. If you are close to the star, well, that's easy. But if you are getting further and further away, you have the radius times the angular velocity, and at some point this velocity will be equal to the speed of light. And so then if you want to go further away from the star and you still want to co-rotate with the star in solar rotation, it's not possible. You are just limited by the speed of light. So in practice, this means that all the field lines that will be crossing this dashed line here that I've shown here, all this field line will not be able to close. So the particle here will not be able to come back to this field line here. What will happen is that it will look more like, so this field line will remain closed, this field line will remain open, and these are the important ones for what's going to happen next, is that all the particles loaded on this field line will be able to close, so at some point you will build up a plasma and then nothing happens. You have enough plasma, there's no electric field. On this open field line, it's a different story, because this one, the plasma is free to stream along the field lines, but they are not going to come back here, or at least not right away. So it means that the plasma is free to go. And so if, imagine you produce a cloud of pairs, this cloud of pairs is going away, then you're going to build a vacuum again, and you're going to start to inject new particles, and the cascade will be sparking again, and so on and so on. So it means that these field lines will be active, in the sense that it will be continuous acceleration of particles there. So this open field line will not look like this, because these ones are closed, but they will look more something like this. They will start to open up, and what is not easy to see in this, what is not seen in this diagram is that they will also wind up. This is actually the dominant process. They will open up, but at the same time, they will start to wind around the star. So you will build up a toroidal field. This is always what you expect if you have a rotating body. The size of this region, of this active region, is called the polar cap size, and with this will determine, in fact, the total energy potential drop that you can get, that you can extract from your pulsar, the maximum one. So you cannot get you cannot get a particle from here to the equator. You will not have the full potential of, I told you, is 10 to the 18 volts, but you will have, in fact, much less. You have a fraction of the polar cap, of the potential drop you can probe. So if you take this fiducial case I've showed you before, it would be 10%. So instead of 10 to the 18, you will have maybe 10 to the 17. The other element that is important here, that will play a very important role, in fact, for what's following, is the region in between here. You see that the magnetic field in this diagram here is changing polarity, both in the toroidal and in the polaroidal direction. But just in the polaroidal plane, like we are here, it means that it is a jump. I'm passing from one plus B naught to a minus B field. So in between, I have to have a region where I'm switching from one polarity to the other. And this region is supported by a current sheet. You have discontinuity in B, you necessarily have to have current to support this discontinuity. So the analogy is what we see on Earth, magnetosphere. you have the field length are stretched, in this case, by the solar wind, but at the back of the magnetosphere, the field lines are being stretched, and you have a region where the two polarities meet, and you have a current sheet, and we see acceleration of particles. So it's a very kind of similar process happening in a high-energy compact object. And the last element, before I move on to more like the modeling, is the electric current. So remember, you have the neutral side is a battery, if you want. Okay, you are polarizing it. Rotation is maintaining this potential difference between the pole and the equator. So you have an engine, you have a battery. And when you have a battery, it means you have an electric circuit that is where you have your plasma that is conducting the electric current. And so you may wonder, okay, but then how is the current closing in the system? Well, there is this current sheet that is carrying current. But where is the current returning back? Well, it's returning back by the polar cap. So you have a circuit that looks like this. It's closing back here. So you have also a current sheet here and here. They are called the separatrix current sheets at the edge of the closed field lines, the outer edge. And all these field lines in dashed are like all the return current. So you will see that we can capture all of this with the simulations. Now, going back to more what we're interested in. We see gamma rays. Where do they come from? We don't really know, but we have some, there are some models that are in the market for more than 30 years. One of the kind of natural idea would be, oh, well, it comes from the polar cap. We know there's an electric field here that must extract the particles. Well, yes, but the problem is that this, the gamma rays that we see is far too energetic. It will be killed by the magnetic field. Remember, it's absorbed by the magnetic field. So it cannot be there. It has to be further away. There is this other model called the outer gap model that is pushing the emitting zone further away, close to this kind of returning current layer over here. And last, which would be in fact the dominant in what we see in simulations, is this current sheet, so outside the light cylinder. So how to solve this? How to say, okay, which one is which? We have to do simulations because unfortunately this problem is too complicated. There's too much plasma physics, if you wish. And one way to solve this problem was done using MAG simulations in a very specific regime, a degenerate regime called force-free regime. And for the first time, this was solved for the axisymmetric case. You can see on the left, this is a result of the simulation. It's not a sketch that I've done by hand anymore. The polaroidal field lines, the light cylinder is over here. And this was done in 1999 for the first time. So it's fairly recent. And for the three-dimensional misaligned case, so the magnetic axis is here, the rotation axis over there, this was in 2006. But the problem is with MHD, first of all, you assume that it's ideal. There is no dissipation there, or if there's dissipation, you put it by hand. You don't really know what's going on in the region of interest. And more importantly, you have no idea what's the energy of particles in there. You have no information about the particles. If you want to go beyond that, you need to use different numerical methods, and which is the method I'm going to explain now, which is called PIC simulations. PIC is for particle in cell simulations. So it's a way to capture physics at a more fundamental level, where you're going to model now the plasma not from a fluid approach. You're not going to average over momentum. You're going to say, okay, my plasma is composed of discrete particles, electrons, positrons in our case, and electromagnetic field. And these two evolve together. And the way we do this is that imagine you have a grid like this with some cells. You're going to inject particles in this box. So here there's maybe 30 that I've put here. In practice, there are hundreds of millions, billions of particles in a realistic simulation, not realistic, in a real simulation. And on top of this, you're going to solve. So you're going to solve the equation of motion for all these the particles, so just the Lorentz force, Newton's law, and you're going to solve the Maxwell's equations E and B on the nodes of this grid. So you're going to involve the particles; they are free to go anywhere, the trajectories, and you're going to solve for the electromagnetic fields on the grid. And so in practice, a loop in a computer will look like this in all PIC code. You will solve the equation of motion of particles, knowing E and B, electromagnetic field. Then you will compute the current that is produced by this plasma as it moves, this current J. And then you will inject this J into Maxwell's equation, this current density, and you will evolve the E and B. So you have a feedback from the plasma motion and the Maxwell's equation. In this way, you can solve self-consistently the dynamic of a collisionless plasma dominated by the Lorentz force. So it means that in our case, we can really solve the acceleration of particles and more importantly for observation radiation. I'm going to now show you how. So just a few more words before we move on to our case of interest, that these methods are used for more than about 10 years in astrophysics. The reason is that in astrophysics, we always have the same problem that the scales are too far away from each other. We have the same problem here because we need to solve microscopic scales, the Larmor motion of particles, and macroscopic scales, the neutron star radius in our case. That's why these methods were used mostly to model a small chunk of an astrophysical object, say a small chunk of a collisionless shock, or a small chunk of a reconnecting current sheets for reconnection. But now the problem is global. We need to solve the problem globally. So we have to solve this in a much larger scale. So we need to have a big computer. That's why this thing was done only recently, because we need to have big resources. Okay, so now I'm using this P code to try to solve this, the overall structure of the magnetosphere. How do we do this? You can see on this diagram, typical setup for an axisymmetric two-dimensional simulation, where we will typically begin with the inner boundary of the box for spherical shell will be the surface of the star, where we will apply an electric field that will show the rotation of the star. You have this co-rotation electric field, we'll apply it to the inner boundary of the star. And we're going to put at t equals 0, 0 plasma, and a dipole field. So all the field lines are closed at t equals 0. We are in vacuum, they have no reason to open. And we're going to try to put the outer boundary as far as possible, and in particular as far as possible from the light cylinder. We won't have the light cylinder into it if we want to capture the whole system, or at least all the elements I've showed you before. And we're going to inject particles from the neutron star surface, assuming either that there is a very efficient cascade or not. So you can play with that, with the injection. I will not go into the details of this. This is quite technical. If you have questions about how we inject particles, we can discuss offline. What now you're looking at in this movie is the time evolution of such a simulation in two-dimensional. And what you're looking at is the magnetic field. You see the field lines, the polaroidal field lines, and in color is the toroidal field, the P phi, so out of the plane. And the colors show you the change of polarity. So you can recognize here all the elements we've seen before in the sketch, okay? But now it's in the simulation. You see the closed field line region over here. The light cylinder is here. And you see all these open field lines. And you see the current sheet. You see it's not perfectly flat. There are some instabilities. I will come back to that. That are due to plasma processes. If you look at the current, it looks very much like what we were discussing before, is that you have this positive current going outwards through the current sheet, and you have this volumetric return current going back to the polar cap of the star. So we can capture all this battery, all this current flowing into the magnetosphere. I'm going to show you the density of the plasma. I think that's the only moment where we show you the actual density. So lots of things are going on, this pair creation here. Again, I will not discuss this matter here, but you can see that we can capture self-consistently the formation of the current sheet. It's all done self-consistently when it's not put by hand. You see it's very time evolution, and here we can capture some of these processes of the sparking. So you have lightnings basically happening in the polar cap of the star. You have a little zoom up here of the polar cap. These are global quantities. Now we want to see, okay, we want to know the answer, where and how particles are accelerated. The answer is summarized here. This is showing you, this is a cut from a three-dimensional misaligned rotator, so the general case, where you can see in every cell, the color shows you the average energy, or here actually the Lorentz factor of the particles in the box, in the simulation. The light cylinder is over here, and right here is the current sheet. So only the current sheet is shining on these accelerating high energy particles. So we can tell, okay, what's going on is that the main acceleration process is relativistic reconnection. There is magnetic reconnection, it's dissipation of this current in this region. So same as what you would see in the Earth's magnetosphere or on the solar corona. Now, on the right-hand side, what you can see is the mean energy of the radiation now. And what we can tell from this is that these particles here are shining through synchrotron process. So we can tell two things, that magnetic reconnection seems to be the dominant process for accelerating high energy particles in the system, at least the highest energy particles. And the main processes seems to be synchrotron radiation. Let's see more specifically what we are looking at here. You can see here the overall Poynting flux, so the electromagnetic energy that the star has, a function of radius. And if I go away from the star, you see that this energy is decreasing. So I'm losing Poynting flux. But I'm not losing it, it's not going anywhere, it's going into the particles. You have a 30% drop, and with this simulation, you can capture this channeling of this energy from magnetic to particles. This is all done self-consistently, and also radiation in the end. Let's look in more details at what particles are actually doing. Now we're going to look at individual particle trajectories, a function of time, once the magnetosphere is already well set up. Oops, sorry, I don't know why it paused. All right, so you see the, no, you don't see. That's a pity. First time he's doing this. What you would see is something like this. This is a summary of all the particle trajectories. All the particles are basically following field lines. All these ones are flowing outward in the form of a wind. All these ones are just trapped. And all of these ones that are interesting for the acceleration are the ones going to high energies. And you can recognize, just by looking at trajectories, all the different elements of this current sheet and this wind region. Let's see if the electrons is doing the same, or actually the electrons is a bit more interesting, so perfect. The electrons, that's too bad, okay. So what you would see also is that the electrons are not just flying out. Some of them that are captured by the current sheet are returning back to the star. They're captured by the star, so I would do an electron. I'm flowing from here, I'm hitting the current sheet, and I'm flowing back towards the star. And these are the ones that are going at high energy because you have an electric field there. It's pointing actually towards the neutron star that is accelerating the particles. That's why we have acceleration, pushing the positrons away and sucking in the electrons. If I look at the typical trajectory, it will look like this for the high energy particles, and I can probe a significant fraction of the potential drop. It can be sometimes 10 to 20%. Okay, so you can really get to very high energies for the particles. So time is running, so I'm going to maybe skip this, and I'm going to go to the high energy radiation. So with the same simulation, we can now compute the radiation. How does it look like? The simplest case to consider is to look at the high energy flux coming from the aligned rotator. This is a three-dimensional simulation, but this is an aligned rotator. You see the magnetic axis in blue is aligned with the rotation axis well, the way around, in red. And what you can see in color is in every cell, in 3 dimension, the flux of high energy gamma rays. The light cylinder, by the way, the edge is here. So everything is coming from the current sheet. The most interesting case is the case of a misaligned rotator. Most interesting because it looks like you need to have a non-axis symmetry. It's not supposed to jump like this, but there's a non-axis symmetry in order to explain pulses of light. If you have something axisymmetric, you're done. There's no pulse of light. And what you are seeing here is the current sheet as well, which has this strange shape, which results from this misalignment. And you can see other things. There are some features over here, some irregularities that are due to plasma processes, instabilities. And one of them is called the Turing mode, which means that it's going to produce some little plasmoids, little island of plasma and high energy particles. And in the movie that I'm going to show you next, which I hope will work, it's going to be a cut through the equatorial plane. So the current sheet will look like a line, a spiral. Okay, this I will skip. Okay, that's what's going on. So we're now looking through the equator. You see the plasma being fed into the magnetosphere, and there you go. You see, you don't have something smooth, you form some plasmoids. And this is very reminiscent of reconnection. This is one of the signatures of reconnection that we already know from previous studies, local studies, that we see happening here, which has also a signature on what you see, some pulse-to-pulse variability. But let's come back, let's try to get closer to observation now. Remember, we have a telescope, we are looking in a given direction, we cannot probe all the directions, we just have one. So it means that I can see only the light that is going towards me. So it means that what you've seen before was photons that were shining in all directions. But in fact, due to relativistic effects, relativistic particle is boosting photons in their direction of motion. So if I have ultra-relativistic particle, you can say, okay, it's going along the particle trajectory at a given time. It means that if I'm an observer looking in this direction here in the equator, if a particle is going in this way, the photon produced by this particle will also going in this way. I will miss the photon. And since this problem is actually very radial symmetry, just by the symmetry of the problem, I will see only a particle going in my direction, which are in fact here. Okay, I will see photons that are aligned with me. But then why do I have this strange shape here? Is because you have to take into account the time delay effect. Okay, because the photon emitting here, when they arrive at me, this phase already rotated. Okay, so you have to take this into account, and that's why you have this strange shape over here, which is extended, by the way, meaning that I have photons being emitted at different places, and they, as an observer at a given phase, at a given time, I see photons that were emitted at different time. Okay, and they just all arrive at me. It's called the caustic effect, like in classical optics, when you have a different path of photons and they all converge, they arrive at the same time in the same place. That's the idea, that you have a caustic effect that is enhancing the amount of photons you have at a given phase. This was, again, the boring case, the aligned rotator, because this doesn't change as function of time. I have the same amount of gamma rays, or slightly the same. But now if I have a real case, which is supposed to be shown here, let's see, maybe it will decide to show up or not. Now if you are looking at, yes, it does. You're looking now at the misaligned rotator, and now we are the observer. We are the observer, so the arrow shown before is here. And we are collecting the light, the flux, as function of phase, or as function of time, if you wish. And you see this extended region in size changes. Well, it's jumping again, sorry about that. It's changing size as function of phase, meaning that we're probing more or less amount of this current sheet. So if we are probing a lot of the current sheet, so if a lot of the current sheet is going in my line of sight, I see lots of gamma rays, and the rest of the time I don't see anything. And by construction of these current sheets, by the shape, just by the shape of the current sheet, I know that there are necessarily two pulses of light. One first pulse of light, fortunately you don't see the second one, but the first one when the current sheet was there, and there's going to be another one where you see the beginning of the second pulse of light. So you can show this in just in one plot for different inclination angles of the magnetic axis. You see phase or time, and you see here the viewing angle. So if I'm a telescope, I will have just one viewing angle. I will cross here, and I will see two pulses of light. See, 1 and 2 in most cases, but not always. If I look at very high oblique angle, I can have just one, or a very bright one, and not so bright second peak. Okay, I'm kind of running out of time. I will go quickly to what we can do beyond this kind of more general picture into closer to observations. I will go a little bit faster, but if you have questions, let me know. We can reproduce kind of different morphologies that we see in the data. Not all, I will come back to that. If I'm an observer looking here, around the equator, I will have two nice, bright, symmetric peaks, separated by half a period. Remember this beam at 180 degrees? This is how it comes from in the simulation. That's how it's built. Now, if you go to higher and higher latitude, you start to form something more and more asymmetric. And to the extreme case, we have just one big pulse of light, and a little smaller second pulse. Now I'm going to present quickly some results that I've been doing with two Master 1 students, where they've been trying to, so first, Aloïs de Vallon, I've been working on trying to fit, so we have all this catalog of light curve possible from the model, and how does it fit with observation? So we have all this light curve from the Fermi-LAT. How do they compare with the observation? Can we explain this? Can we reproduce some of them?
Is the solution unique?
Right, so there are some degeneracy. In particular, when you get to the oblique case, as you get more and more oblique, there's many solutions that are degenerate. So it's not perfectly one-to-one correspondence, but we can tell quite well what's the obliquity angle, which is the interesting, because the viewing angle, okay, well, it's just the way we are, but the obliquity angle is more physics in there. And in this case, there's much less degeneracy in the solution. And so what we found, so you see a couple examples. It does not always work very well, but in most cases, I've tried to show some of them. You see one peak, double peak, two peaks with some bridge emission. So red is the simulation, and in blue is the gamma ray data. We've done this for the second catalog, which is 100 pulsar, 117. And what we found, I think the key finding that we have here is that we find that if you look in different beam in age of the pulsar, we find that systematically the young pulsar are more misaligned than the old pulsars. So it seems that there is some sort of alignment of the magnetic axis with the rotation axis with time. And we can measure this characteristic age, which is roughly 100,000 years to 1,000,000 years. And it turns out that similar studies, but using radio data, seems to indicate a similar alignment process with a slightly, I think, higher age, but I think it's more closer to 1,000,000 years, if I remember correctly. And the other interesting case is that if you look at the very young one, there seems to be more like kind of randomly distributed in obliquity angle, like as if at birth, the magnetic obliquity angle didn't take any preference, but it was kind of randomly distributed. Okay, and I will finish with the last diagnostic that we can do, which I think is pretty convincing for validating such an approach, and I think will be more important in the future, is to try to look at polarization of light. And the reason is because polarization of light is very sensitive to the geometry of the magnetic field. So if you are emitting light perpendicular or aligned with the field line, the local field line, you will not have the same polarization signal. And so we thought, well, we could try that and see if we can explain the only case where we see we can measure polarization in optical, which is the Crab flare, the Crab pulsar, and see if we can understand this. It turns out that in optical, the light curve is almost exactly the same as in gamma rays. It's almost no difference. It looks like this. So it is a gamma ray, but I could show you the optical. I'll show you later. These two pulses of light, and we say, okay, which solution fits the best? Where I have a separation phase of 0.4 between the two, and a factor of 3 between the main pulse and the secondary pulse. Well, it turns out that for in this case, to come back to your question, the solution is not degenerate. There is a unique solution for this case, and the parameters are roughly an inclination angle of 60 degrees and 130 degrees viewing angle. So we are looking at the pulsar like this rotation axis, magnetic axis, and we're looking somewhere like this, if you follow me. And we say, okay, so with this solution, can we understand the polarization signal? This is not the simulation, this is the data, and you can see how beautiful this is. This is in a diagram which shows you the Stokes parameter, which basically shows you how polarization works. So just, it's very simple to see that each time, so you see the color is the phase in time, so you see the two pulses. So you have the main peak, so you're doing like this for the first peak, then you're coming back at the center, and then you have a second peak, and you're doing another loop. The loop is telling you that the magnetic field, with respect to the emitting zone, is flipping from one polarity to the other. At each time you pass through the current sheet, sorry, this is my interpretation, but this is from the observation. The magnetic field line is flipping from one polarity to the other at each time you pass a pulse of light. You see, you have one swing, then you go back here, you stay with the same polarity, and then you have a second swing. So this is just, just to give you the two elements. You have the polarization angle gradient here, and you have the polarized flux. And that's what we get for this parameter. We got this is the same idea that you have a first loop here for the first pulse, and then you have a second pulse of light, and you have a second loop. In fact, we've done the other way around. We looked at what was the best diagram, which one was fitting the best the diagram that we see in polarization, and then we inferred the light curve. And we did the other one, and I will show you. And this is very robust, and this is a very strong criteria to look at polarization because it's very sensitive. You go to a slightly different parameter and it will look different. What is very robust, however, is the loops. You will always have a swing of the polarization angle. And the reason is very simple to understand because in the current sheet model, from what you get in the simulation, is that the current sheet is passing towards you. You see a pulse of light. But by construction, the current sheet is separating, it's between two polarities of the magnetic field, right? So necessarily, you will probe one polarity, you cross the current sheet, and you will switch to the other polarity. So you have, by construction, a way to have a swing that is natural from the simulation. Okay, I will wrap up here by just saying that simulations really played an important role for going further into our understanding of the magnetosphere of pulsars and in trying to understand the basic plasma processes, simply because it's too complicated to do this analytically. There were lots of expectations that were confirmed, other surprises. And what we can confirm is that the current sheet is playing the major role in the acceleration process and for the emission of high energy radiation. So I think there's more to do in particular this injection physics of particles. So there's more details to look into this. Understanding the radio emission in particular, it's actually much more complicated than the gamma rays. And also something that I'm currently involved in is trying to understand now the most inner region of a black hole magnetosphere, because there are similar issues that are still unknown. Is okay, how do you extract this energy in the form of energetic particles close to a rotating black hole? But this will be for later. And thank you very much.